Okay. Okay, so hello everyone. This is the NPTEL course Functional Analysis. Analysis Problem Solving session. We are in week 12 now. I think this is the last week. Okay. And I'm Pawan Kumar Raikowal. Okay. So in this session, we are going to discuss some problems from the 12th assignment, so that will help you to solve the problems by your own remaining problems. Okay, so let's get started. Okay, so question number one, let V and W be Hilbert spaces, and V1 through Vn be a collection of vectors in V, and Wn through Wn be a collection of vectors in W. And we have defined a mapping K from V to W as this. Then which of the following statements are true? First says K is a continuous linear function from V to W. Okay, let's see this. Okay, uh, mapping is defined as, okay, is it linear? I think linearity is very easy to check. I mean, it's just inner products. If kx with y, then it will be, yeah. So additivity is straightforward, and even if you take multiples, okay, linearity just follows from the definition of inner products. Okay, the inner product is linear in first coordinate, hence k is a linear operator, and continuity also follows from the Cauchy-Schwarz inequality. So I think linearity we don't have to check. Yeah, it's straight away. Then is K a compact operator? Yeah. So what is the definition of a compact operator? Can anyone tell me definition of compact operator?
Sir, dimension of range of T is finite, sir.
No, no, that's the reason here that it's compact. But what is the definition of compact operator? And when do you say that a operator is compact?
The image of every bounded operator set in V is relatively compact in W, sir.
Ah, okay, yeah, that's what I wanted. Okay. So what we in other words, what I mean equivalent definition is the image of closed unit ball is relatively compact. That's what we need. Yeah. So if you consider now a finite rank operator, I mean any operator T suppose is of finite rank and continuous, then what we need, if you just take the image of a closed unit ball, suppose I'll call it B. B is your closed unit ball. So T of B is again, what do you say, bounded. Yeah. And now if you take the closure of T of B, it is going to be T of B again. Why? Because the range is finite dimensional. Yeah. So in a finite dimensional space, every subspace is closed. Yeah. So from that, what do you know? Image of a closed unit ball is again closed and bounded. Hence, in finite dimensional space, closed and bounded set is compact. So it's relatively compact. It's in fact compact. So we are done. If the operator is what do you say, finite rank, then it's compact. Okay. Okay. So any problem in that?
No, sir.
Yeah, finite rank operator is compact. And the only thing we have used is infinite dimensional space, closed and bounded set is compact. Yeah, the closure of T of B is a closed and bounded set, hence it's compact all the time. Yeah. Then third, is K injective? Okay, what can you say about this option? Anyone from the audience? What do you have? Balu P. Karta, can you participate in the discussion? Okay. So what happens if K is injective? Then we know that dimension of kernel of K will be less equal dimension of range space of T, which is suppose n, I assume. Yeah. So then it will imply that the space V is finite dimensional because of rank nullity theorem. Yeah, because what do you know is the range is finite, range space is finite dimensional, null space is finite dimensional, so space has to be finite dimensional. Yeah, but this is not true in general because you can think of infinite dimensional vector spaces whose range is finite dimensional. Yeah, so this is not true. In fact, what do you know is null space of K, we'll say in the question number 2, it is the span of, I mean, it is the birth. So this need not be 0, yeah? I mean, if V is infinite dimensional, then this is non-trivial all the time. So first C is wrong. We don't need this page. Question number 2, let V and W be Hilbert spaces and K belongs to, just a minute. Yeah. So V and W Hilbert spaces, K be an operator of finite rank. Okay, it's almost similar to the first one. Okay, you have given a finite rank operator now, and then you have defined the orthogonal basis for the range of K, which of the following statements are true. There exists a collection of vectors v1 through vn in V such that x. Okay, you have this representation. Okay, let's see. Option A. Okay. So, anyways, if W1 through Wn is an orthogonal basis of range space of K, then what do you know? Kx is always we can write as summation inner product of Kx with Wi, right? Going from 1 to n. This is just the representation in orthogonal basis of any vector. Yeah. What you want is you want to replace this term with inner product of x with vi. You want to find a suitable vi's. Yeah. What we do is we just define a linear functionals phi i's from say V, the space is V, yeah, defined as phi I of x equals to inner product of kx with wi. So these are the linear functionals for each I, and V is the Hilbert space. So by representation theorem, for each I, there exists element Vi belongs to V such that phi I at x equals to inner product of x with Vi. Yeah, this is by Ray's representation theorem. We know this thing. So now, but how? What is phi I of x? This is inner product of kx with wi. So see, from equation 1 and 2, we got kx equals to summation. I can replace inner product of kx vi with inner product of x with vi. So this is what we wanted. Is it okay? Any doubts?
No, sir.
Okay. So option number 1. Okay. When the dimension of null space of K is equals to n. Yeah, again the same thing. Now we have the range space as finite dimensional. If you have the null space also finite dimensional, then the whole space becomes finite dimensional. But we need not be finite dimensional space here, right? So this option is wrong. And the third one, that null space of K is Z perp, where J is span V1 V3 up to Vn. Okay, let's see. So how is Kx defined again? See, if x belongs to Z perp, then this will imply inner product of x with Vi is 0. Yeah, for all I from 1 to n. So if this is 0 for all I, then this 0, 0, 0. So this kx will be 0, right? Ultimately, this implies kx will be 0. Then this will imply x belongs to null space of k. This follows straightforward. But is the converse also true? Yeah, I mean, this right now just implies that Z perp is contained in null space of k. Yeah, we want to see if the converse is also true. So like if x belongs to null space of k, this will imply kx is 0. That is summation inner product of x with vi wi is 0. But this is what? This is just a linear combination of wi's, right? Which is 0. But wi is an orthonormal basis. That means it's linearly independent. That means the scalars has to be 0. So this means inner product of x with vi has to be 0 for all I. But then this will imply x belongs to Z perp. Means null space of K is same as Z perp. Okay, I hope it's clear. Yeah, we can interact if any of you have any doubts in this. We can. I mean, this is easy. In fact, I don't think there's any doubt. I'll just go ahead. Okay, question number 3. H be a Hilbert space. V1 through Vn be a collection of vectors in H, and W1 through Wn be a collection of linearly independent vectors in span V1, V3, Vn perp. Okay, I mean, just to stick to the notation, we'll again call Z as this thing span. You can say this is very similar to the question number two. I mean, all the setup. G is V1 V through V and perp, and this Wi is this belongs to. Oh, sorry, this is just G. This belongs to G perp. And we have Kx defined as W. So what do you know? Null space of K is Z perp. Also, range space of K is just span of Wn, which is again contained in Z perp. Correct? From this. So what can we say about uh, eigenvectors or eigenvalues? Suppose if I want to say. I mean, if suppose if lambda is an eigenvalue, that means there exists some let's say x or okay, I'll call it v such that kv equals to lambda v, correct? But then this will imply v belongs to range space of k. This will imply v belongs to null space of k. But then this will imply kv is 0. But v is non-zero. This will imply lambda has to be 0. Yeah, are you seeing the arguments? Because range space is contained in null space of k. Yeah, that's the reason this is all working out. Hence, this means the only possible eigenvalue of k is 0. So, for I plus alpha k, what do you know eigenvalues of I plus alpha k? I mean, simply spectrum of I plus alpha k will be 1 plus alpha times lambda, where lambda belongs to spectrum of k. Yeah, this is what we know. And this is never going to be 0 because k, uh, I mean, for the eigenvalues at least, what we know is eigenvalues also follow the same things. Hence, because alpha is all the time 0, so eigenvalues are only 1. Yeah. Hence, this is going to be injective all the time. This is one method to do it. You can do it by other way also. I mean, yeah, if you try I plus alpha k of x is 0, this will again imply the same thing. Alpha kx equals to minus x. This implies yeah, alpha is given non-zero, right? For every scalar. Okay. Yeah. So if alpha is 0, then this is just identity operator. So no need to check. Identity operator is 1 1. So if alpha is non-zero, then kx equals to say minus 1 by alpha x. So again, same method. X belongs to the range space, hence kx has to be 0. So if kx 0, x non-zero, then alpha has to be 0. Uh, sorry. If kx 0, uh, okay. Let me check. What we want to prove that I plus alpha k is injective. So if this is 0, I need to prove that x has to be 0. Okay, how does this follow now? X belongs to range space. Implies this is 0. Yeah, okay. Yeah, because now x belongs to the range space of k, which is same as the null space of k, hence kx has to be 0. But kx is minus 1 by alpha x, which is 0, and alpha non-zero, this implies x is 0. And this is just, playing with the arguments. And the very important argument is this. So either way you do by calculating the eigenvalues or by explicitly finding out the null space of I plus alpha k, which is singleton 0, that means I plus alpha k is injected. Okay, is it clear? There was some.
Yes, sir. Clear, sir.
Okay, that's good. So what do we have for every scalar alpha? The operator I plus alpha k is injective. Now option B, for every scalar alpha, the operator I plus alpha k is invertible. Okay. So I plus alpha k, first of all, belongs to set of all linear operators from V to W, and both V and W are Hilbert spaces. So both are Hilbert spaces, Banach spaces. So it is enough to show that I plus alpha k is bijective. Is it correct? Why is it enough to show that it's bijective to show it's invertible?
Sir, we have to prove I plus alpha k is invertible, so it is enough to prove it is bijective.
Yeah, why? I mean, if it's bijective, we just know that the set theoretic inverse exists. But why do we know that the inverse is again continuous? It follows from the bounded
What
inverse
is the
theorem.
mode?
Yeah, it follows from the bounded inverse
Oh,
theorem that you have a bijective map from a Banach space to Banach space, then the inverse is again continuous. Okay, it follows from. Yeah, because when we say invertible in LBW, we mean that it's bijective and inverse is continuous. Yeah, that will be the definition for inverse. Okay, so is it bijective? You can refer to a lecture in, I don't know, first or the second lecture of this week where sir had explained the Rees-Fredholm theory. So in that there was a statement that if T is compact, then I mean from, okay, this is a symbol for set of all compact operators. V and W are Hilbert spaces. Then null space of T minus I or I minus T, you can say, is zero if and only if range space of I minus T is whole W. Yeah, if I remember correctly, this was the statement.
sir, range of I minus t equal to V, sir.
No, no, my operator is from V to W. The range will be a subspace of W, and it has to be surjective.
Okay, sir. Okay, sir.
Is it okay? I mean,
Okay, sir.
maybe
Okay, sir.
maybe in the theorem, sir has used the same operator, some same space V to V. Okay, is it necessary to use the same
Yes.
space? In the question, what
Yes.
do we have here? Oh, sorry, here we have the same space. Yeah, sorry. Yeah, I guess it's necessary to have the same space. Yeah. Okay, thank you. Thanks for the remark.
Thank you, sir.
Yeah. Uh, this we want. This is the Rees-Fredholm theory. Okay. So here, what we have is the operator K. Yeah, the operator K we have is finite rank operator. So this will imply that K is compact. Yeah. But then by Rees-Frodom theory, and also we have proved by one part A that I plus alpha K is injective, right? And
Yes, sir.
alpha K is compact. Then by, I mean, this implies that null space of I plus alpha K is zero. Then by Rees-Frodom theory, range space of I plus alpha K whole V. That means it's surjective. So one we have proved, and surjective follows from Rees-Frodom theory, and by bounded inverse theorem, inverse is continuous. Hence, I plus alpha K is invertible for all alpha scalars. Yeah, so this gives you correct answer for the option B. And yeah, so then option C will be wrong because it puts a condition on alpha. Like it says I plus alpha K is invertible only if mod alpha is like has this bound. But this is wrong. I mean, even if it doesn't have this bound, we have proved from part B that it's always invertible. Okay, so is it clear? Okay, I think it's clear. So we'll go to the next question. Question number 4. Okay, HB Hilbert space and K from H to H be a compact operator. Which of the following statements are true? If K has closed range, then it is of finite rank. Okay. Okay, so K is from H to H. Both are Hilbert. I mean, H is a Hilbert space. Okay. We have a compact operator and its range is finite. Okay, so what can you say? Do you have any guesses or any way to go for this question? The range is closed, so you can say that the range space is itself a Banach space. Yeah. So bounded inverse theorem maybe is, I mean, any guesses or any clue? Can you try? Okay.
No, sir. No, sir. You explain, sir.
Okay. Okay. So we'll go. So we'll take maybe W as the range space of K. Yeah. So now we have given that K has closed range implies W is closed. Okay. Now this operator K will be from H to W. Yeah. This is compact and onto. Correct. Okay. So It has to be okay. But it need not be 1 1. I was thinking about taking the inverse, but because if inverse exists, then we know that it's continuous, and then if you composite it with k, then it will give you the identity operator. Then we are through. But the inverse, but this k operator need not be 1 1. Okay, somehow we have to create some kind of right inverse or left inverse. Just a minute. I have to put charge to my laptop. Just 1 minute.